Perfect.
And the right size.
To avoid the
3 generations of warming up garbage collection.
We will talk to you about that
Yeah.
as you are.
Okay, shall we kick this off?
Yes, sir.
Okay, well thanks everybody for coming, and I think more people will trickle in as they get here. My name's Dave from FoundationDB. We've got another Dave from FoundationDB there. We've got Stephen, Will, Nick, and Ian, and we're gonna just spread ourselves out and divvy up. And we have our own projects to work on, but we also are planning to do a bunch of chatting with you guys about any projects you guys are working on. What I wanted to do, I guess, is just give you guys a brief introduction to what we're trying to accomplish at FoundationDB and sort of what the product does today. FoundationDB, as you can tell by the name, is like a database. But the way that I usually explain it to people is not as a database, but as a storage substrate. So when I think about a database, I might as well draw because I've got a whiteboard. I think about a few tiers usually. You have your query language and your API at the top tier of your database. So for a SQL database, right, for a SQL database, this is going to be SQL, right? That's how you interact with it. For something like MongoDB, this is going to be your Mongo API. It doesn't have a nice name brand on it, but it's going to be queries on documents, selectors on documents, stuff like that. Sort of the second tier of the database is what I'll call the data model, which is sort of physically what is this database storing. And in a SQL database, of course, you have tables. And in a Mongo database, you have documents, right? One level down from that is what I'm going to call the storage engine. Storage engine. And in SQL, for example, in MySQL, we have InnoDB. And the abstraction here actually for InnoDB is of an individual table. An indexed table is the basic abstraction that InnoDB works with. And in Mongo, again, you have, this doesn't have a name, but this is the Mongo storage engine. It's their own distributed storage engine. So normally a database, when you pick a database, you pick all 3 tiers at the same time. You're picking an API, you're picking a query language, you're picking a data model, and you're picking a storage engine. The whole sort of philosophy with FoundationDB is to build this. Build a really, really amazing storage engine or storage substrate. And try to build it in such a way that you can actually build different data models, query languages, and APIs on top of it. So what we've come up with is an ordered key value, transactional, API. So this is the basic fundamental abstraction of what FoundationDB is. So a key value store, let's start at the simplest part, just means that FoundationDB associates a binary key with a binary value. It's totally agnostic to the kind of data that's in there. The ordered is that it sorts all those keys and values lexicographically, sort of by key. And the ordering property is crucial because you can do efficient range operations. So clearing a range of data, or reading from a range of data is a single operation on the database and tends to hit a single machine in the cluster. So if you read a range of 100 values, it doesn't actually have to go to all 100 machines in the cluster and bring them all back. Those will tend to be co-located. The most exciting part of what we're doing is the transactional. Because the transactional is where the ability to build these other tiers comes from. So if you just have a key value store and an ordered key value store, the problem is you start putting your data into keys and values, and you come up with something like you want an index on something, right? So let me draw up some keys and values. No, I'll be fine. So if I say like David equals green and Ian equals orange and Will equals green, and these are like favorite favorite hair color, or something like that. This is a key and a value, key and a value, key and a value. So now we have a really simple way using our key value store that we can look up somebody's favorite hair color. The sort of obvious thing that you want to do with one of these things is you want to build an index on it. So you want to say, you know, I want to find all the people with green, like green hair, find all the people with orange hair. And you can't do that except for by scanning through the data. So the way that you make that more efficient, and you know, the way SQL database does this, MongoDB does this, is you build an index. And the index looks something like this. Green, I'm going to just use that as a delimiter. Green div equals quote, quote. Oh, sorry, I'm getting ahead of myself. Green will equals quote, quote. And orange Ian equals quote, quote. So what I've done here is I've used what I'm calling a delimiter here. Actually, I'm going to write this a different way. I'm going to write it as a comma. And so when you think of it this way, because it's sorted lexicographically, this green, all these keys that start with green are going to sort together. And all the keys that start with orange sort together. Because this is sort of one of the properties of the ordering, right? Is that any sort of common prefix means that all the keys that share that prefix are in the same place. So when you do things this way, you now have an index where you can do a single range read operation on all of the keys that start with green, and just pull out the list of all the people that have green hair. So I'm doing this to sort of illustrate you how you take a key value store and turn it into a higher level data model, which is like an indexed, you know, key value store with a sort of reverse index on one of the fields. But here's the really tricky thing. If you just have a key value store, when you go to add a new person, okay, I'm going to go put in, I don't know, what do we have? It's John equals blue. Right, so I want to go in here and say blue John equals quote, quote, right? The trick with a key value store is that you actually have to update the actual key and value, and you also have to update the index key and value. And you can't do those and guarantee that those two write operations get synchronized and are atomic with respect to each other unless you have this transactional property. So the really cool thing, so what we're trying to do here is we're trying to take a key value storage engine and talk about how you build a little data model, maybe even a query language, a really simple query language for finding people with a certain color of hair on top of this. And the key point is that you can't really build these abstractions solidly unless you have a transaction which can update both the index and the data together. And so the cool thing about FoundationDB is that it's pretty much the only NoSQL technology out there that has a transactional API. That you can actually do these transactions that allow you to build higher level abstractions, that allow you to build sort of strong guarantees into how your data models are updated. So we sort of talk about this whole idea of how to map your data model and your query language down into the actual keys and values in the storage engine, as we call that data modeling. And there's an interesting guide written by Stephen here on our website and our documentation about data modeling, about how you can take certain common entity attribute value data models or array data models or queues or whatever, and actually relationships, map those down into simple keys and values. But so you can look at that, you can ask Stephen about it, but one of the sort of core concepts is a notion that we call tuples. Okay, so very frequently when you're using FoundationDB, instead of just thinking of the key as a binary piece of data, you want to think of it as an ordered tuple of certain things. And so we have a tuple layer built into FoundationDB. So when you import FoundationDB, you say like import FDB or whatever in Python, you can say fdb.tuple.pack, and you can pass it in a Python tuple or a tuple in whatever language you're using. And
This isn't tuple like RDF tuples at all, though. It's just three things.
Or in-
it is n things, yes.
Okay.
It's n things, and the things can either be basically a string or an integer. Okay, so that's the basic data types that are supported.
Byte string, Unicode string, or integer, I
Right.
think right now.
Right. So a couple different kinds of string, right, or integer. Yes.
Just to complete the picture here, what the double quotes on the right?
Yeah.
What is that typically? What is?
Yeah. So frequently in an index, in the simplest form of an index like this, you actually don't actually store anything over here. And the reason for that is that if we just inverted David and Green, if we inverted, the person in the hair color, we'd be left with multiple keys that are green. So you could be like green equals David and green equals Will. But the problem is in FoundationDB, every key maps to a unique value. So to make the key unique, we append the name of the person onto the end of it, which in a way sort of leaves you nothing to store over here.
Could you store
Now-
a list of stuff on the right?
You can store anything you want over there, right? So if there was another attribute about David, like for example, that this was green and my age was 97, right? And Ian's age was 86, right? Then you could store that information over here if you wanted.
And that's what's called the covering index.
Yeah, depending on your data model, right? And this might give you the ability to, even when you were just doing an index operation, not to have to go back, be like, oh, green, like, oh, David, go look up David, go look up this, right?
Right.
So
And
if that was
somebody
a
asked if-
convenient thing for you, you could store that there.
Yeah. And somebody also asked if you could store the index by saying like green equals like serialized list of primary keys or whatever. Green equals David, Will.
Yeah.
And that is possible. But it makes it a little harder to update fast. So like this is the more typical first go-to for a simple
It's
index.
empty.
Yeah,
Is
Yeah.
the typical
Right.
first.
the thing you didn't mention that you might want to add to your box of 3 points to become 4s, I don't think you said the word distributed yet.
Yes, well this is the API abstraction, right?
So, I think your claim that we're the only ordered key value transactional is,
Well, I said the only NoSQL. Okay, so let me make that clear, right? So yeah, so the API abstraction that you work with when you talk to FoundationDB is an ordered transactional key value. This is a very similar abstraction to if you work with BerkeleyDB or something like that, okay? Obviously, this really special thing about FoundationDB is that it's a fully distributed system.
Yeah, I was gonna ask
It
if
is-
you wanted to put distributed in your little box with your 3
Yeah.
characteristics.
Well, it's a characteristic of FoundationDB, but not of the API, but I'll definitely put it here.
In other words, you don't need to know that.
Yeah, that's right, you don't need to know that.
the API
Um,
in no way betrays that information.
And what we have here, sorry it's off camera, but what we brought is actually a little demo cluster of 5 machines running FoundationDB. And this is running, the real software. It's triple replicated. And we'll show you guys how this all works. You can turn off power to the individual machines and unplug network cables and all of that. But the cool thing that we're trying to build is that from the perspective of the programmer, this thing looks like a single key value store. And if you unplug one of them from the wall, it still looks like the same key value store, right? So coming back to here, just to complete this, I think you guys probably caught this, but the way that we then usually write these in code is that we encode these as tuples. And the tuple layer guarantees that things sort first by the first element of the tuple, and then second by the second element of the tuple, and then third by the third element of the tuple, and so on, which makes it really easy to read all of the keys in the database that share a common tuple prefix, which ends up being a really, really useful common sort of data modeling technique.
There's some other neat aspects of it. The integer encoding of the tuple layer is a variable length encoding that still guarantees ordering across the full range.
Yeah.
Oh, wow.
Yep. Yeah, a lot of that encoding encoding works very well, which is why we tell people just to use that built-in tuple layer rather than try to forge out on your own and try to figure out how to make your own key space that, you know.
The idea of using a delimiter can be useful pedagogically, but then if there's like a byte in the first string in the tuple that is less than the delimiter, then your ordering is wrong, and you know, like
Stuff
that.
like that. So let me tell you the other really common thing that you do with tuples is that very frequently when you're thinking about an application building on FoundationDB or a data model or a little algorithm or something, there's a couple different kinds of data that you have to store. There's like data about users, and there's also data about, you know, keywords, and there's also data about something else. And the way that you attack that problem is just with what we call just like a subspace, which is just a really easy thing to do with a tuple. You can literally even just put it in quotes. And basically, you know, you fill in the rest of this. So what happens with this is that if you put all of your information about users in the tuples that start with users, comma, and you put all of your information about keywords starting with keywords, comma, right? Then it guarantees that those things stay separate, that, you know, any reads that you do on one, you know, don't affect reads on the other one, that, you know, transactions that only touch one don't touch the other. I mean, you know, there's now two separate parts of key space that are almost like two little mini databases themselves. The cool thing, of course, is that they're not two databases, they're part of one database, which means that you can do transactions to the database that modify both of them and guarantee that the modifications are in sync, right? And so that's sort of the common pattern when you're thinking about playing with FoundationDB or building a little abstraction on top of FoundationDB, is you're trying to figure out, sort of you're working your way back up this stack. You're first trying to figure out your data model, and then you're trying to figure out sort of what kind of queries your actual sort of application use case is going to have to service, and sort of mapping those all down into keys and values.
You might, I don't know if everyone here is familiar with traditional NoSQL, how there's like how much you denormalize stuff and how much the data can be in some situations.
Yeah.
So I don't know.
Speak to that a little bit?
Yeah.
Yeah, so, I mean, so normally, again, when you choose a MySQL database, you're normally choosing a query language, a data model, and a storage engine. You're choosing them all together. And since there's no transactional ability, it's hard to build any abstractions, or you can't build your own indexes very easily. So what you're sort of left with is just the data model that the NoSQL database usually just provides for you. So in the case of Mongo, you're sort of stuck with like the notion of a document. And in Mongo, if you want to update one document and another document, you can't actually guarantee that those updates are synchronized with each other, right? So what you normally do with NoSQL is you think about your problem, you go, is it a big column of data? Is it a big table of data? Is it more like, you know, a hierarchy of data? And you actually pick your NoSQL database depending on what data model you need. Because again, without transactions, once you pick a data model, you're really stuck with it. So the whole thing with FoundationDB is to sort of deliver a lowest common denominator API to its storage engine that you can build other things on top of. And this is sort of a point of interest. You sort of go and order transactional key value store, you know, sounds pretty simple. Can you build a really rich thing on top of that? Well, one sort of very interesting thing is that the SQLite database, which is a really popular embedded database, is working on SQLite 4, which is sort of their in development version of it, their next generation. And one of the big things they're doing in SQLite 4 is actually decoupling the storage engine internally from the query parser, planner, you know, and executor. And very interestingly, the abstraction that they chose internally is an ordered transactional key value store. So even from somebody starting with a SQL database from scratch, thinking about a good abstraction for a storage engine, that's what they're picking, an ordered transactional key value store. And we see that popping up. The Google Spanner technology, which is one of the other very few sort of technologies in the universe that we know of that are a real distributed, read scalable, write scalable, distributed transactional system also has the sort of basic abstraction of a transactional key value store. So I do think that this ordered transactional key value store is sort of, it seems like sort of the future, sort of the lowest common denominator, sort of future storage engine API. So it's very cool for us that sort of we chose that sort of in parallel with a few other projects. So just to let you know an example of a really cool hack with FoundationDB. So Dave, who's right here, actually found that SQLite 4 was going to use this abstraction, and he built a SQLite 4 FoundationDB connector. Okay, and what that does is it means that SQLite 4 normally just thinks it's talking to an ordered key value store that is just a hard disk. But what it does instead is it talks to an ordered transactional key value store that's actually FoundationDB. And here's what happens. I'm going to erase. I'll erase this over here. Here's what happens when you do that. Normally SQLite runs up here, and it talks to its storage engine right here, which talks to a hard disk, right? And this is the abstraction barrier that I'm talking about, a transactional ordered key value store. So this is normally on a single machine, right? It's sort of an embedded database. What's really neat is if you rip out this storage engine and plug in a new one that actually doesn't talk to a hard disk at all, but instead talks to a FoundationDB cluster over here. This is just almost like a pass-through, right? Because this is a shim. Then you still have a SQLite database, but it's actually now a fault-tolerant distributed SQLite database, because this is a fault-tolerant distributed storage engine. And here's the other cool thing. It's no longer a single machine embedded database. Because if you run two SQLite instances with two shims pointing at the same database, what you actually have is that because of the transactional properties down here, even if there's two clients doing two transactions at this level that are going to conflict down here, FoundationDB will correctly detect and deal with that conflict and try it again and all of that. So you have true ACID properties, isolated transactions, everything, even across multiple machines running what was 8 hours ago an embedded database, right? So that's the kind of cool thing that you can do with it. Will, who's right here, built. There's a Java graph database called Blueprints, which is on a stack called Tinker. Is it a stack or a company? I don't know. Tinkerpop. The Tinkerpop stack is a Java graph database stack. There's a query language called Gremlin, and Blueprints is the basic database. So Will, in a couple of days, actually created an implementation of the Blueprints graph database on top of FoundationDB. And the process he went through was looking and being like, okay, what are the basic things in the data model? We have vertexes, we have edges, we have attributes of vertexes, we have attributes of edges. We're going to need an index for that. And he basically just went through this process of thinking about the subspaces where you store things and the ways that you index them, and then sort of mapped that data model down into keys and values, and then mapped the sort of Blueprints query language down into sort of operations on that data model. And again, built a fully transactional, distributed, scalable, fault-tolerant, whatever, version of the Blueprints graph database, which passes their entire test suite. So, that's another sort of really cool sort of FoundationDB hack. The whole goal of FoundationDB, the whole goal of this is that to make it easy for developers to build backends, data models, whatever, that inherit these exceptional properties from the storage engine, right? So where you normally use a key value store, build something, you wouldn't really get fault tolerance, you wouldn't normally get transactionality, you wouldn't normally get scalability. The idea is to make it really easy to build a system that has those properties.
Can you just take a minute and speak to the multi-paradigm, like multi-data model opportunity as well
Yeah,
that you've hit on before?
yeah. So one of the big things is that you have total flexibility over data model, which means that you're not locked into one, right? So if you want to use the FoundationDB storage engine to store a high contention counter, as one data model, you can do that. And if you wanted to store a big blob of binary data, like a big file that you could stream through, you can do that as well. But of course, you can do those on top of the same database. So one of the very cool things about FoundationDB compared to a traditional NoSQL database is that often, as your application progresses, you're like, oh well, we've got that message queue thing, and we've got that counter thing, and we've got that table thing. And what you're doing is you end up picking a new NoSQL database for each of those. And we talk to people all the time that are storing like user data in Mongo. They've got some like message data in Cassandra, and then they're using a couple of Redis instances to do a couple of other things. And this is a huge operational burden. For a developer, it's actually not as bad, because the developer just clicks, downloads, starts playing with them, easy API, it's all good. But the problem is when it actually comes time to run these systems in production, they each have different requirements. There's a lot of sort of magic to running each individual one, and it's sort of jointly, it's a real problem. So the cool thing about FoundationDB is that it gives you a storage engine on top of which you can build a number of different data models and APIs that can all sort of run together and consolidate a lot of what you used to have to do with multiple NoSQL databases. So that's the basic introduction to what the product does. Any questions on that?
Sure.
Yeah.
Where shall one not go? For example, if I try to implement a graph database using SQL, it's going to be really non-performant because the lookups are very different than a
Yeah.
graph database. So, is this good for some things and not others?
Yeah, it's a really interesting question. You should probably, since you have like the amazing resource here of having a bunch of people, you should talk to us about anything specifically, but I'll try to speak to it generally. Generally, no. Generally, you can tackle all different kinds of problems. And the trick is mapping it down into keys and values. One of the key properties to being able to say that we can do a lot of different things is the ordering property, right? Because fundamentally, like streaming reads are pretty different operation than random reads. And certain database technologies are built to only be good at streaming reads. And some are only built to be good at random reads, right? Like if you distribute every key according to a hash of the key to a machine in a big cluster using consistent hashing or something, you cannot do range reads efficiently, right? On the other hand, if you store your data in a huge, compressed column, you can't do individual inserts, reads, random reads and writes efficiently. So FoundationDB basically is pretty good at both of those cases, right? It's pretty good at range reads, and it's pretty good at random reads and writes. It ends up having to do with the size of the keys and values. Let me explain that. If you are building an application that's going to be scanning through a lot of data, and you want that to happen efficiently, you probably want to try to store your data in slightly bigger chunks of key value pairs, right? You might put a few K of data, like a K or 10K maybe even of data in the value, so that you weren't having too much overhead of reading a lot of individual and parsing a lot of individual key value pairs, right? So for applications that you know are going to be streaming data, you choose a slightly different sort of packing into keys and values than applications that you knew were going to only be doing random reads and writes. But there's a lot of flexibility. For example, let's say that you know that your application was going to be doing a lot of random writes and a lot of streaming reads. And you weren't going to do the opposites, you know what I mean? You weren't going to do streaming writes. So you could probably come up with some data mapping that worked really well for that. And basically, if you can dream up how you build a data structure using normal sort of pointers and objects and all of that, if you can dream up how the data structure would work, that's probably approximately how it would map down into FoundationDB keys and values, if that makes sense.
And you built the blob layer. We talk about certain data models kind of as layers, the idea being that they're not intended to be necessarily like the final form of something, but merely a utility that builds on top of the key value pairs and provides a new facility or a different efficiency. And so the blob layer is a way of representing objects that, like files, let's say, like a big chunk of data for an image.
Yeah.
You expect to be larger than sort of the recommended value size. And a neat thing that you can do in the layer is, from a programmer's perspective, you think of it as the programmer can ask for a blob by a key and get back a thing that they can ask to read a section of or overwrite a section of or append to. Behind the scenes, the blob layer can do some nifty tricks. Like it can start storing data in large chunks, but as it notices that you're treating different areas of the blob differently, behind the scenes it can make runtime decisions about how it's going to to mutate.
Where it's going to split, where it's going to coalesce, all of
Exactly.
that, right?
So it's not even like you have to make, again, you don't have to make a fixed decision going in. It's just like, I'm going to do this. You can write logic that can be very adaptive.
Yeah, and I built the blob layer, which was used for doing large object storage. The representation is a arbitrary length, sparse binary object. So you resize it to a terabyte instantly, and then put data in as you want. Ian took that thing and was like, hey, we have blobs, like why don't we build a file system? So Ian built a Fuse file system on top of the blob layer that probably isn't the recommended way to boot your machine, but but works. So again, a lot of possibilities there. Yeah.
So the indexing there, is that, I get the impression that you can define your own algorithm for indexing things that are inserted, is that?
Yeah, you basically can. You guys can also, you guys, everybody can use the abstractions and layers that people like us have built, right? So if you want to think about blobs, you can download a little blob Python file or whatever and use it. But when you start from the storage engine itself, you have complete flexibility about how to define things like indexing.
Right.
Because
and
there's
also
no
complete responsibility for doing it.
And responsibility.
Okay.
There's no indexing built into that core, right? Again, the key enabling thing for indexes is the ability to wrap everything within a transaction, right? So you say begin transaction, update the data, update maybe many indexes. You might update 10 indexes of the data, indexed on different things, and then say end transaction commit, right? And that's the really powerful thing that lets you build those indexes and bake them into an abstraction that you build, right? Versus having to sort of hand the responsibility even one level up. Yeah.
So I guess, one of the reasons that a lot of those SQL databases like Cassandra or HBase went to a giant row model is that joins are very expensive in a distributed system. Do you guys, are they, I imagine, have you guys done anything to solve that problem? If I have,
Yeah, good question.
if I have a class and I want to get all 500 students and they're kind of all over your cluster,
Right.
is there any tools I could use to co-locate those on one
Right.
for efficiency or is
Yeah, so it's a good question. So again, the core doesn't have any technology to do joins in it because it's really dumb. I think what you said there is the one of the key points, which is, in any join operation, they can be really complicated. There's something that's happening down at the physical level, right? And you sort of have this intuition, I think, which is just right on, which is that you don't want to have to go to a million places and do a million operations. You want to sort of somehow get it co-located, and this is how you do that.
Oh, okay.
Ordering.
So things are put on the distributed based on the order. They're not.
That's
it's not
correct.
logically ordered. That's actually physically ordered.
That's correct. What's happening at a physical level is that the database, all the keys in the database are being split up into chunks, which represent, consecutive regions of key space. And those chunks are being automatically replicated and divided and partitioned across the machines in the cluster. So if you have an intuition when you're thinking about your query language and your data model that you're frequently going to be accessing a group of keys together, what you're trying to think about is how are you going to make them share a prefix? How are you going to make them share the most specific prefix that you can? Because that's going to then map down into a really efficient single range operation. And one thing that I'll point out is that there's sort of what I think of as almost like abstraction of indexing, sort of meta-indexing or something. An index is sort of this simple thing. One thing you can do with FoundationDB is that if you have an API up here where there's, you see just that there's like 4 or 5 operations that are sort of like, just let's say they're read operations, and you're like, look, I can't think of any one data model where those are all going to be like some range read, because they're just very different kinds of sort of operations. You can literally just be like, okay, what n representations of the data do I need to cover all those API calls, right? And again, with transactions, when you go to update the data, just make a transaction and update each of the n representations of the data, and then end the transaction. And if you do that, you're guaranteed that all those representations will always stay in sync. And then when depending on what actual sort of API function call you're using, you can go and use the representation that makes it be a single efficient operation.
So one other thing to add, is that when you are forced to go do 500 reads or whatever, all of our APIs provide asynchronous, reads, so that you can do those all in parallel really easily. And there's you can do those 500 reads and have them all back in a couple of milliseconds. So it's increasing the load on the cluster. It's more expensive than reading all those 500 things in a range from one place. But latency-wise, it's not too bad.
So from the client perspective, I hit one of the things in the cluster. I guess I have a choice whether I block for that data back.
Right.
Yeah, the way our APIs usually work is they return you like a future. And when you want to convert the future into a into an actual value is when it will block or whatever.
Right.
So you can ask for a bunch of things and then block.
Yeah. For example, if you say like a equals get a, and b equals get b, and then c equals a plus b, right? That will actually, just if you write that code, and this is actually fdb.get, right?
Sure.
Depending on the language, that will actually, this will not block.
Okay.
It'll return immediately, and this will be a future version of that value, which will actually wait until you actually use it in something before it blocks on it.
Okay.
So if you do get A, get B, it will be done, and they'll shoot out in parallel. And then when it says, oh boy, I need to use them both, it will then block on them both coming back.
And that's implicit in some languages, and in others you have to say a.get and b.get or whatever, depending on
the API,
what the language supports.
how powerful it is. So yeah, let me tell you what we were hoping to accomplish today. Mostly we wanted to come down and meet you guys. We all have a bunch of projects. There's 6 of us, are there? Yeah, I think there's 6 of us here from FoundationDB. We all have some projects that we were excited to hack on for a day, but we wanted to introduce you guys to this technology and provide as much or as little help as you wanted, learning about it, trying to play with it, answering questions about NoSQL databases in general, sharing our knowledge that we've built over the last sort of 4 years of working on this project. So that's our basic agenda, and if we walk it away at the end of the day with either some of us or some of you or both having built a couple of cool little layers or abstractions or a little demo on FoundationDB, so much the better. Does that sound good?
Yeah.
Awesome. Okay.
Alright, I wanna talk to someone about it.
Well, I'll just let us break then and get into it.
By the way, I'm not a developer, don't ask me anything.
You fake it pretty well.
Yeah, I was gonna say, by the way, he's the business guy, but he's